Okay, so now what we want to look at is standard called IPSec. Okay, now so far in all the classical attacks and even in the man in the middle attack, the main reason that people were able to launch all those attacks is what I said is due to IP spoofing. You can make the receiver to think the message came from a particular sender if the receiver sees the IP address of the sender in the message, but the message would have really come from somebody else. So how can we avoid this? So that's why we need to look at this IPSec standard. Using this, you can really avoid IP spoofing. Of course, it comes with the overhead, as we will see. So the way we do this is before the sender and receiver start their communication by sending the data messages, they really need to establish what is called an IPSec security association. Okay, so they need to go through a kind of message exchange process in order to establish the IPSec security association. And this is a broad overview of that process. So we are not going to go into the very details of this. So the first step is for the two end hosts A and B to exchange their public key certificates. So we are looking at this at the host level. So as I said, the computers, the host can also have their public key certificate. So that needs to be exchanged first between the two end host. So the public key certificate will have the IP address and the public key of that host. So host machines can also have their own public key and private key. So in the public key certificate, the IP address of the host and its public key would have been digitally certified by a certifying authority. So that means that whatever is in the certificate is a genuine IP address and public key that is certified by the certifying authority. Okay. Now, so all further communication will be encrypted with the public key of the receiver. So that means once each side gets to know the other host public key certificate, they will use the public key of the receiver to send the message. So if A wants to send something to B, A will encrypt whatever it wants to send with the public key of B, so that only B could decrypt that message with its private key and process it. Nobody else can see what it is. And A will use the right public key of the receiver B, which was taken from the public key certificate of B. So A is not using Mallory or somebody else's public key, so it is using the right public key. So that is the idea here. So basically, so IPSec is standing on the top of this public key certification idea. So that's why we saw public key certificate also already. Okay, so now for the actual communication. So they have exchanged the public key certificate. So now for the actual communication, again they want to provide this confidentiality, integrity and authentication. So in order to provide confidentiality, we need to use some symmetric encryption algorithm or basically some encryption algorithm, right? So if you use symmetric, then you have to have a secret key. That's typically what it is used. So in order for them to use a symmetric key encryption algorithm, they have to agree on a secret key. So as I said, there is less security if the two end hosts use the same secret key for all their communication sessions. So it's better they establish a secret key for each communication session. So that means for each session they have to establish a secret key, and the way this is done is before establishing a secret key for that particular session, they'll establish what is called a session key. Okay, so there's two layers of communication here, or two levels of communication. So you first agree on a session key that is supposed to be used for the session. Again, there is a method called Diffie-Hellman key exchange process that can be used for two sides to really agree on a particular key. So that's the idea behind Diffie-Hellman key exchange. They will exchange some messages to agree on to use a particular key as a session key. And again, for all these things, the messages are encrypted with the public key of the receiver, as I said earlier, so nobody else could hack the channel and see what is being communicated. So once they agree on a session key, they'll use that session key to establish a secret key that can be used to do the symmetric encryption for providing confidentiality in the communication. Now they also can do what is called use keyed hashing algorithms. So keyed hashing is nothing but what you have seen so far. Like this is keyed hashing. So you generate the hash value of the message, you encrypt that with a certain key. So that is known only to the sender. So you could encrypt with the private key of the sender, or you could encrypt the secret key that is known only to the sender and receiver. So either way, that is called keyed encryption, keyed hashing. So again, there are a lot of algorithms to do this. So as part of this security association establishment process, the two end hosts will have to also agree on the algorithms to use, because a lot of algorithms out there. So the two sides will have to agree on what algorithm to use to provide confidentiality and what algorithm to use to provide integrity and authentication, because each side could be capable of using some algorithms. So both sides have to agree on what algorithms to use for each of these features, for guaranteeing each of these features. And as I said, they can go through the Diffie-Hellman key exchange to establish a session key, and through that to agree on a secret key. So they have to go through all these things to before they can really start sending any data. So once they agree on a secret key, they can use that with the algorithm agreed for symmetric encryption and start exchanging messages that provide confidentiality. And again, depending on what keys they have agreed for providing authentication, they can also use the agreed upon algorithms for providing integrity and authentication, and then do the corresponding processing that will provide integrity authentication. So once they agree on all these things, they can start sending the data messages. Now also this security association is kind of unidirectional. So that means if two machines A and B want to send messages in both directions, then they have to establish a security association in each direction. So we say a security association from A to B is said to be outbound at A. So it is A to B, so it's outbound at A and inbound at B. Now also this IPSec security association can be kind of globally unique because each security association is identified with a tuple, which is called the security parameter index and the IP address of the outbound of the sender. So this is from an IPSec association from A to B. So the tuple will have the IP address of A and the security parameter index that is locally unique at A. So that is like a 32-bit quantity that we'll see the details as we proceed. So a security parameter index is something that is locally unique only at A. But when you combine that along with the globally unique IP address of the host machine, the whole tuple becomes globally unique. So that's why we can identify an IPSec security association in a globally unique format using the security parameter index locally generated at the end host along with its public IP address. Okay. Let me make sure I am saving this. Okay. Any questions so far? Okay. So there could be two variations of IPSec header. So I said this is like an additional thing you have to incorporate for every message you're sending. So you have what is called an IPSec header that will feature the information required to provide confidentiality, integrity, and authentication. So you place the IP header in between you place IPSec header in between the IP header and the transport layer header, followed by the data. So typical transmission, you will have the IP header followed by a TCP or UDP header and then the data. So you place the IPSec header in between the IP header and the transport layer header. Now there could be, depending on what are the features you want. If you want only integrity and authentication, we could use a variation of IPSec header called authentication header. Okay, it's called AH in short. And if you want all the three, confidentiality, integrity, and authentication, you could use a header called encapsulated security payload header, and in short it's called the ESP header. Okay, and we'll see how they look like very soon. Now also you need to understand that who is supporting this IPSec standard. So would all routers be able to handle IPSec or only the end host? Now, if the end host can handle IPSec, okay, they need to be able to establish an IPSec security association between the two end hosts, and that way message is secure all the way from the sending host to the destination host. Okay, so that the header look like this. You'll have the IP header which has the source IP address and destination IP address and all the other information that you saw in the IP header. Then IPSec header will really have information pertaining to a security association established between the ultimate source and destination. So this is assuming the end host can themselves be able to establish a security association and take care of handling IPSec. But not all end hosts will be able to do that. So if the end host can do that, it's called the transport mode. Okay. Now, as I said, not all end hosts will be able to do that. So we could have the gateway routers at the sending network and the destination network to be able to handle this. So if the gateway routers are handling this IPSec, then this is called tunnel mode. So that means you will have the original IP datagram that the sender wanted to really send it to the destination. So you have the IP header, the normal IP header, with the IP address of the source and IP address of the destination, along with say the TCP header as the transport layer header, and then the data. So this is similar to the IP in IP encryption that we saw in some earlier modules. So here, not encryption, IP in IP encapsulation. So what you do is you encapsulate this IP datagram inside another IP header. So the outer IP header will have the IP addresses of the gateway routers that are responsible to handle this IPSec. So we'll have the IP address of the gateway router at the sending network and the IP address of the gateway router at the destination network. And you'll have an IPSec header that will also correspond to the IPSec security association established between the two gateway routers. So this is how the message is going to be transmitted in the public internet, appearing to actually go from this router R1 to the router R3. So this could be actually even encrypted to provide confidentiality, so nobody can see what is inside the data. So the routers in the internet will just look at the IP header and forward it. Okay, so this is called the tunnel mode, and this process is called also the IP in IP encapsulation. Okay. Now, how does the IPSec header look like? So again, we are not going to get into the details, but let us just see an overview. So this is a normal IP datagram with the IP header has a source IP, destination IP, and the next protocol following the IP is the TCP. If you use TCP as a transport layer protocol. So in the IP header, there's an 8-bit field called the next protocol field, and you include in that the code corresponding to whatever the transport layer protocol is. If you use TCP, use the code for TCP. I think it is 6. If you use UDP, use the code for UDP, which could be 17. So use the corresponding code, and then you include the data, which is the payload that you really want to send. So this is a normal IP datagram. So now if you look at how you incorporate the IPSec header, as I show here, this is placed in between the IP header and transport layer header. And for the authentication header, this is how it is done. So the authentication header is placed in between the IP header and the transport layer header. So this is the IPSec header in between, and again it has various field information, and the one we are interested here is the security parameters index. As I said, it's a 32-bit field that is unique for each security association. The sender can locally make it unique. to whichever destination it's communicating. So all security associations that are originating at a particular sender will have a unique security parameter index. Then for that particular security association, as you send the messages, each message could have a unique sequence number. And again, this sequence number is different from the sequence number used at the transport layer. This sequence number is to keep track of the messages at the IPSec level. And now if you do not use any IPSec, the next protocol field here is TCP, corresponding to the transport layer header. Since here you are using the next protocol header is the IPSec header, and this is actually corresponding to authentication header. There is a code for authentication header, and that's what you should indicate in the next protocol field. And in the authentication header, there is the next protocol field, and there you indicate TCP, indicating to the processing side that after the IP header, the next protocol header to be processed is the authentication header, and after it, the next protocol header to be processed is the TCP header. Now, what are the things I have colored here in yellow? So, remember to provide, so authentication header provides integrity and authentication. And what is that you use to provide integrity and authentication? If you remember this method that we saw, you basically compute a hash value of some message, and you encrypt the hash value with a key that is known only to the sender. So that is what you want to compute here. So you use all these yellow colored field values to compute the hash value. So you compute the hash value based on the information in all these highlighted field values, and then you encrypt that with the private key of the sender. Okay. Now that is what is called the authentication data. Okay. So what are the field values that are used to do this to compute this hash value? So you notice here the things that are used are the version field, the header length, the packet length, the ID, which is the for fragmentation purpose. If you remember fragmentation, the source IP, destination IP, and all this thing. Now the field that is not used is the TTL field, and the fragmentation field like the offset field, and the more fragment flag, do not fragment flag, and the checksum field, and so on. Now if you think about it, the difference between the field values that are highlighted and those that are not highlighted is this. The ones that are not highlighted are the ones that change at each hop. Each router will be able to decrement the TTL field and of course compute the checksum and so on based on the updated TTL, and include that in the checksum field. So you want this to be done only at either the ultimate end host, source and destination, or the end gateway routers. No intermediate router should be able to change or do anything with IPSec header. So that's why you compute the hash value, which is the authentication data, only on those field values that will not change during transmission. Okay, and you again include you encrypt the hash value with the private key of the sender. So that is supposed to be known only to the sender. So if you let any router to handle it, the router will not know the private key of the sender. So that is why use only those field values that won't change during transmission, and compute the encrypted hash value only at the sending side. Okay, so that's the purpose of the authentication header. Now the ESP header, which is the encapsulated security payload header, it's not really very straightforward like this, where the authentication header is in between the IP header and the transport layer header. The ESP header, as the name indicates, it encapsulates the payload. So that means the ESP header, which is this highlighted blue area, includes the TCP header and the data. So that's why it's called encapsulated security payload. So it will encapsulate the payload and the TCP header. It also has the security parameter index and sequence number field values. Now if you see here, the next protocol field is the ESP header, which is this, and following the ESP header, the next protocol is the TCP header, which is actually inside the ESP header. Now here the yellow colored area is what is really encrypted for confidentiality purposes. Again, the key that you use for confidentiality is to be agreed upon by sender and receiver. That is supposed to be established as part of the security establishment association establishment process. Now the blue colored area is what you use for computing the encrypted hash value, which is called the authenticated data. So you see what is being used in the authentication header is different from what is being used for the ESP header to compute the authenticated data. So for the ESP header, you don't really use anything from the IP header, whereas in the AH header to compute the authentication data, you use a lot of field values from the IP header. So that's also a difference between the two. So here the authenticated data, which is the hash value, is computed based only on the SPI, the security parameter index, and sequence number. Of course, the security parameter index is supposed to be known only to the sender. It's locally unique to the sender, so it is supposed to be known only to the sender. So sender can only insert that value. And also for every data packet that you send as part of the security establishment, you increment the sequence number. You also, like in TCP, start with an arbitrary sequence number in order to make it difficult for someone to hack the channel and guess the sequence number. Okay, so these things only the sender will be able to typically include them and compute the encrypted hash value. Okay. And for the confidentiality, you use only the payload typically and the TCP header. That's really the information really you want to maintain the secrecy for. Okay, so that is how we provide confidentiality. Alright, so any question on IPSec, you can ask over the microphone or enter any message. Let me save this.